So in the previous part, we have studied method of determining a least square approximation, but this method possesses the disadvantage of solving a large linear system of equations. We have all the linear system of equations and we need to solve them. And this system has the issue that if a small change in any of the parameter, it leads us a large error in the entire solution. And this condition of that error is known as ill conditioning. So instead of solving this least square problem with this method, we have an alternate method, and that gives rise to orthogonal polynomials. So this is one concept which we are going to see. So what is orthogonal polynomial? So first of all, let us choose one approximation. So suppose y of x equals to a naught f naught of x plus a1 f1 of x plus up to so on an fn of x. So suppose this is your approximation, and what is this f0, f1 and fn? So this fj of x is a polynomial of x in degree j, polynomial of x which has a degree j. Okay, so now we can write s of a0, a1, a2 up to so on an as we have the formula a to b w of x, that is work, then y of x minus a0 f0 of x plus a1 f1 of x plus an fn of x whole square dx. Okay, so this is the equation for s of a0, a1 up to so on n. Now we need to find a condition so that this s is minimum. So we will do is we will find partial derivative of s with respect to a0, a1 and an, and we will equate it with 0. So deva s upon deva a0 equals to 0. So what's the value of deva s upon deva a0? We have already seen that it is equal to minus 2 a to b w of x y of x minus a0 f0 of x plus a1 f1 of x plus up to so on an fn of x f0 of x dx. Okay, so this is the partial derivative of s with respect to a0. Similarly, we will find partial derivative of s with respect to a1 and equate it with 0. So we'll get minus 2 integral a to b. Similarly, w of x into y of x minus a0 f0 of x plus a1 f1 of x plus up to so on an here also it's an fn of x into f1 of x dx. Okay, so going in this manner, continuing in this manner, we'll get deva s upon deva an, which is equal to 0, and it is equal to minus 2 a to b w of x into y of x minus a0 f0 of x plus a1 f1 of x plus an fn of x into coefficient of an is fn of x, so fn of x dx. Okay, so these are the required condition for s to be minimum. Now with the help of this we will get the normal equation. So what are the normal equations? So normal equations, I'll just directly write down, no need to by heart this or as such. So directly it is a naught into integral a to b w of x f naught of square x dx plus a1 integral a to b w of x f naught of x into f1 of x dx plus an integral a to b w of x f naught of x into fn of x dx. Okay, so this is equal to integral a to b w of x y of x into f naught of x dx. Okay, so this is the first normal equation. Similarly, the rest of them are a naught integral a to b w of x f1 of x f naught of x dx plus a1 integral a to b w of x f1 of square x dx plus an integral a to b w of x f1 of x fn of x dx, which is equal to integral a to b w of x y of x into f1 of x dx. So such that the last normal equation will be a naught integral a to b w of x fn of x f naught of x dx plus a1 integral a to b w of x fn of x f1 of x dx plus an integral a to b w of x fn square x dx, which is equal to integral a to b w of x y of x fn of x dx. So these are the required normal equations. Now this normal equations we need to simplify them because they are larger than what, like they are we need to simplify them. So instead of writing all this in, we can write it in terms of j. Okay, so let's see how we can write. So now we can write a naught integral a to b w of x f naught of x fj of x dx plus a1 integral a to b w of x f1 of x into fg of x dx plus an integral a to b w of x fn of x fg of x dx, which is equal to integral a to b w of x y of x fj of x dx. Okay, so we have just simplified it and we have written this in terms of j. So fj of x fj of x, so j goes from 0 1 to up to so on n. Now this whatever the fj of x, whatever we have found, that f naught of x f1 of x up to so on fn of x. So whatever this f naught f1 and fn are, these polynomials are known as orthogonal polynomial. Orthogonal polynomial. If they satisfy one condition. Okay, so what is this condition? So it is integral a to b w of x fp of x into fq of x equal dx should be equal to either 0 if p is not equal to q, and the other one is integral a to b w of x fp square of x dx if p equals to q. Okay, so this is the condition and if it satisfied any of the f naught, f1, fn of x satisfies this condition, then these polynomials are known as orthogonal polynomials. And there are different types of polynomials. They are orthogonal polynomials. So orthogonal polynomials. So what are these orthogonal polynomials? The first one is Jacobi. Okay, so first name is Jacobi, and next one is Chebyshev, and we need to study this Chebyshev polynomial, and this is in our syllabus. We need to focus on this. There are two kinds of Chebyshev polynomial. First kind, and the other one is Chebyshev polynomial of second kind. The Chebyshev polynomial of second kind. Okay, now next one is legendary polynomial. Then we have language, and last one is Hermite. So these are the types of orthogonal polynomials. We will concentrate on Chebyshev polynomial of first kind. We don't have Chebyshev polynomial for second kind in the syllabus, and this Chebyshev polynomial is of the form Tn of x, and its interval polynomial lies in the interval -1 to 1. So its domain is this. Okay, so now we will see Gram-Schmidt orthogonalization process. Consider the proof of this theorem, that is Gram-Schmidt orthogonalization process. So suppose that phi naught of x star equals to 1 and phi 1 star of x equals to x minus a10 phi naught star of x. Okay, so first of all we need to consider this basic approximation, that is phi naught star of x equals to 1 and phi 1 star of x equals to x minus a10 phi naught star of x. So now we will have to find the value of a10, and we need to which is a constant. Okay, so this a10 is a constant, and first of all we need to consider that phi naught star of x. So before that we need to consider that phi naught star of x and phi 1 star of x both are orthogonal to each other. So if phi naught star of x and phi 1 star of x are orthogonal, then what we'll get is their integration a to b w of x phi 1 star of x dot product with phi naught star of x dx will be equal to 0. Okay, so now we'll substitute the values of phi 1 star of x in the above equation. We'll get integral a to b w of x minus a10 phi naught star of x into phi naught star of x dx equals to 0. Okay, so in the next line we'll get integral a to b. So now we need to multiply this x with phi w of x and phi naught star of x. So we'll get x into w of x phi naught star of x dx minus integral, this minus integral over a10 phi naught star of x into w of x into phi naught star of x dx. So we'll get a10 phi naught star square x into w of x dx, which is equal to 0. So we'll consider this whole term to the right hand side. So we will get integral a to b x w of x phi naught star of x dx
equals to, now we can take this a10 outside because it is a constant term, so which is equal to a10 integral a to b w of x phi naught star of star square of x dx. Now we need to find this value of a10, so we'll take this entire integration term to the left hand side, so we'll get integral a to b x w of x phi naught star of x dx upon this integral, so integral a to b w of x phi naught star square x dx, which is equal to a10. Okay, now we know that we have taken the approximation as phi naught of x star equals phi naught star of x equals to 1. So substituting the values of phi naught star of x as 1, we will get as integral a to b x w of x dx upon integral a to b w of x dx equals to a10. Okay, the reason is phi naught of star of x equals to 1. Okay, so this is what the value of a10 is. What we'll do is we will find the value of a20. Again, to find the value of a20, as we had considered phi naught star and phi 1 star, here for a20 we will consider two polynomials, that is phi 2 star of x and phi naught star of x. So let this two be orthogonal to each other, and phi 2 star of x will be orthogonal to phi 1 star of x. So we'll make use of this two conditions to find the value of a20. So as phi 2 star of x is orthogonal to phi naught star of x as well as phi 1 star of x, what we know is, therefore integration a to b w of x, their dot product, that is phi 2 star of x dot with phi naught star of x, will be equal, dx will be equal to 0. So again we will repeat the same procedure. So now what we'll do is we will define phi 2 star of x, which is equal to x square minus a21 phi 1 star of x minus a20 phi naught star of x. So this is a second approximation. We will consider this case and then we will solve this. So substituting the values of phi 2 star of x in this equation, will get integral a to b w of x square minus a21 phi 1 star of x minus a20 phi naught star of x into phi naught star of x dx, which is equal to 0. I've just substituted value of phi 2 star. Then next one is, again we will separate the integration for the above, so we'll get a to b w of x into x square into phi naught star of x, so it is into x square phi naught star of x dx minus integral a to b, again w of x multiplied with this term into this, so we'll get w of x or a21 into w of x phi 1 star of x into phi naught star of x dx minus integral w of x into this a20 phi naught star of x into phi naught star of x. So a to b a20 w of x phi naught star square x dx equals to 0. Okay, so now this will become So as this phi 1 star of x and phi naught star of x, they are orthogonal to each other, their dot product will be 0. So this entire term will exit, so this value will be equal to 0. So what we are left with is integral a to b w of x square phi naught star of x dx minus integral a to b a to 0 w of x phi naught star square of x dx equals to 0. Again we'll shift this entire term to right hand side. We will get integral a to b w of x square phi naught star of x dx, which is equal to integral a to b a to 0 w of x phi naught star square x dx equals so dx. So again we can take this a20 term outside because it is constant. So a20 outside, so integral a to b w of x phi naught star square x dx, right hand side as it is. So this will have x square phi naught star x dx. So now we will take this in the denominator. So we will get integral a to b w of x square phi naught star x dx upon integral a to b w of x phi naught star square x dx, which is equal to a to 0. So now the values of again phi naught star of x and phi naught star of x and phi naught star square of x equals to 1. So this will give you integral a to b w of x dx upon, so into x square. So this x square into w of x dx into w of x dx equals to a to 0. This is the value of a to 0. Again, so next what we are going to do is we will have the dot product of phi 2 star of x and phi 1 star of x. So similar process for w of x phi 2 star of x dot with phi 1 star of x equals to 0. Again we'll substitute the value for phi 2 star of x. So what we'll get is integral a to b w of x into x square minus a to 1 phi 1 star of x minus a to 0 phi naught star of x into phi 1 star of x dx, which is equal to 0. So again separating the integration, we will get integral a to b x square w of x phi 1 star of x dx minus a to 1 integral a to b, so phi 1 star square of x into w of x dx equals to 0. Again this phi naught star of x into phi 1 star of x will be 0, so the dot product is 0. So I have not written the term directly, we can write this two term only. So now again a to b x square w of x phi 1 star of x dx, which is equal to a to 1 a to b phi 1 star square of x into w of x dx. So to find the value of a to 1, we will get a to 1 as integral a to b x square w of x into phi 1 star of x dx upon integral a to b phi 1 star square of x into w of x dx. Again, so this is the value of a to 1. So now we will generalize this So generalizing it, we can directly see that if phi I star of x equals to, now if we see that values for phi 1 x, phi 1 star of x or phi 2 star of x, we can see that it starts from x raised to I minus a10 phi naught star of x minus a I1 phi 1 star of x minus up to so on I minus 1 phi star I minus 1 x. Okay, so now orthogonalizing phi I star with all the phi naught star of x, phi 1 star of x up to so on. So what you'll get is AIR equals to integral a to b w of x raised to I into phi star of x, phi r star of x dx upon integral a to b w of x phi r star square x dx. So let's see with respect to a to 1. So a to 1, here 2 is your I and 1 is your r. So with respect to this, what we got is integral a to b w of x. So we will see this with respect to a to 1. So here 2 equals to I. So I equals to 2 and r equals to 1. So this is equal to integral a to b. Now x raised to, what we got is I. So here I equals to 2. So x square into w of x phi, whatever the value of it is, r. So it is given as 1. So phi r star of x. So phi 1 star of x dx upon integral a to b w of x into phi r star square of x. So r value is 1. So phi 1 star square of x into dx. So in general you can write this. So this is the generalization. So we will see one example so that it's easy to understand. So we'll see one example so that it becomes easy for you to understand.